welcome to the Naive Bayes talk. So basically, we'll get started. It won't be a very long session, probably like 10-15 minutes max, not a big topic. But essentially, Naive Bayes is just a classification algorithm, just like how you have stuff like logistic regression for classification. And it's just based on Bayes' rule. So what that means is it assumes that the features are conditionally independent, and that's why it's called naive Bayes, because in reality that's very much not in most situations that's not the case. The features are indeed related and influence each other, but if we ignore that fact, then it makes computations a lot simpler, and that's what naive Bayes does, makes it much easier to compute and much more scalable as a result, which is why it's so widely used. So as you can see on the screen, we have Bayes' rule over here. It's written in a slightly different format. This one's to do with classes and feature vectors. Just letters are different, that's all. And what each part means, if you want a refresher on Bayes' rule, is that so the first, what we're working out is actually the posterior probability of class X given the feature vector X. Class C given the feature vector X. And what that means is the posterior probability is the most likely. It uses the distribution once you have factored in the data and the prior distribution as well. Whereas the prior distribution is something that you believe beforehand before observing the new data that you can see. So, going on to the next part, the probability over here, the first term, X given C, is likelihood of feature vector X given the class C. So how likely is it that we observe the data that we have observed, given that this is the class, for example, and then multiplied by the probability of C means the prior probability of class C. So what did we believe before was the likelihood of, or the probability of being in class C without this new data that we've now seen. And finally, the denominator here is the probability of X, just simply the marginal likelihood. And it's also just called the evidence. We'll see what this means a bit later. It will make more sense. So the first step in naive Bayes is the training phase. So what happens in the training phase is for each class, you compute the prior probability and the conditional probability of each feature. So that can be represented using the two equations that I have. These are basically the two equations that you need. You don't really need anything else. And it'll make more sense once I go through a walkthrough example of how this works. And then obviously the second phase is just the prediction. Based on some kind of threshold, you can make a prediction from the probability that you get from the classifier. Now, basically, we have a walkthrough here. So, naive Bayes for disease diagnostics. Some of you might recognize the question. It is from one of the tutorial worksheets. So, if I go through the question, it says, a medical test is used to diagnose a rare disease based on two symptoms, fever and cough. The model uses a naive Bayes classifier, and the probabilities of the symptoms appearing given the disease status are, and then there's the table here. So, we can see that they've given us the probabilities of the symptom occurring given they have a disease and also given that they don't have the disease. And these are the symptoms here. So another fact that they tell us is that we know that only 5% of the population has the disease. This is what we call the prior probability. And it was the second term in the numerator of the Bayes equation. And it's because this is what we're already going to assume before we've looked at the new data. So what do we have to do for this question? So the tasks are, 1, to compute the probability that a patient with both fever and cough has the disease, and to classify that patient as having or not having the disease. And then we also have to explain what the naive Bayes assumption is and why it's important. So that one's just going to be a word question. So let's look at the biggest part and probably the most important slide of the presentation, this worked example. So how we will tackle this question, it's fairly basic, simple, it only requires like 3 steps. We will look at the Bayes rule, right? As we saw at the start, I've pasted it back in over here. So the disease, so we want to work out, as the question asks, the probability that a patient with both fever and cough has disease. We can write this as what is the probability they have the disease given that they have a fever and a cough. That is what we want to work out for this question. And with Bayes' rule, as said above over here, we can split that up into the probability they have a fever and a cough given that they have a disease, multiplied by the prior probability, meaning the probability that had disease, which we've been told in the question before. Finally, over the evidence, and by the evidence it is just the probability they have the fever and the cough, regardless of given that they have a disease or not. So I hope it's clear where this target equation comes from. From that, we can then get we can now start to work out the various terms we need to get the answer. So the first term that we needed in this is the probability they have a fever and cough given that they have a disease. So this is a joint probability, obviously, which means since we're assuming each feature is independent, we can just split it up into the probability they have a fever given they have a disease multiplied by the probability they have a cough given they have a disease, due to the independence assumption, obviously. So if they weren't independent, you wouldn't be able to do this since they would be conditionally dependent on each other. But yeah, if you go back to the table, the probability, given that they have a disease, the probability of fever is 0.8, the probability of cough is 0.6. So if you multiply them two together, you get 0.48, and bam, you have the first term. Next term, probability to have a disease, easiest one of all. We've already been given that in the question. Probability that the general population has the disease is just 5%, so we already know that to be 0.05. Now, this is the more trickier one, is the evidence. So the probability they have fever and cough. So probability they have the fever and cough can be is essentially this equation here, where you have to sum the individual probabilities of them having a fever and a cough given they have a disease and given them not having a disease, multiplied by their weight, aka how much of the population we expect to fall into that class based on prior knowledge. So the probability they have a fever and a cough given that they don't have the disease is simply just no disease. They have a fever, probability is 0.2, cough probability is 0.3, meaning if you multiply them together, you'll get this probability of fever and cough given that they don't have a disease. Then the probability of no disease is 0.95. We just did 1 minus 0.05 because if 5% have the disease, that means 95% don't have the disease from the population. And that's all we need to kind of work out the probability of fever and cough, since we just substitute these values in here. So we get 0.48 from there multiplied by the weight, which is the probability of having disease, which is 0.5. And we add in the ones that we worked out now, given that they don't have a disease. So we have 0.06 multiplied by 0.95. These are just the weights, by the way. It ensures that we're proportionately taking into account each probability, and that gives us 0.81. Now going back to the original rule over here, we have all the terms we need to actually just do the math. So here, the probability that they have a disease, given that they have a fever and a cough, can be boiled down to 0.48 from there, multiplied by 0.05 from here, divided by 0.81. Sorry, 0.81. Is it 0.81 or is it 0.081? I think it's 0.081. I'm just going to verify that I've got that correct. Yeah, so if we look at that, it's actually 0.81 here, meaning I worked it out right. Okay, so 0.81. No, yeah. So no, sorry. Okay, so this is 0.81. Sorry for the typo. and it gives us the answer of 0.29, not 0.029, and that is less than 0.5, which is the standard threshold for a classification algorithm. Hence, the model does not classify the patient as having the disease. And that's this question. That's about like as bad of a question you're probably going to get on naive Bayes. It just takes you through the entire classification mechanism from the data to some predictions. Then here's a more theoretical question. So it asked, what is the purpose of the assumption? What is the assumption? So the naive Bayes assumption is that the features are conditionally independent, meaning here that having a cough has no effect on the probability of having a fever or vice versa. The reason this is misleading is because in reality we know it's not true, as you're much more likely to develop a cough if you have a fever and vice versa. Just ask Shay, he's had it for like 2 weeks now. And yeah, that's about it. That's about it for naive Bayes. It's a small topic, just a classification algorithm. Is there any questions regarding anything that I've gone through? It's fairly quick and stuff. Any questions? Classifier when we have multiple classes. How do we compute the class label there? Okay, yeah, so let me show you that here. Essentially, if you have multiple classes, can I zoom in on this? If you have multiple classes, you can do so like this. So you can just keep multiplying it by... Oh, sorry, you mean like multiple... So yeah, if you have it, is this what you mean? Does this answer your question? Sorry, I don't know if I got your question correctly. Are you asking about this? You just keep multiplying them together, the various probabilities. Can you share the window on OBS too? Yeah, that make... Oh, did that not go onto OBS? Okay, I will make sure that goes onto OBS as well. Actually, so, I'll just add it as a window capture, I guess. Notion. Yeah. So here you go. That is now also on OBS. Cheers for that reminder. Okay, Danny's question. So choosing a class because it is greater than 0.5 is the same as choosing it because it has the highest probability, right? But we are just assuming 0.5 because there are only 2 classes. So not necessarily, yeah, it's not necessarily the case with that one. So it's not to do with the number of classes, it's to do with a threshold that you set in your algorithm. Normally you do pick the class with the highest one, but in this case, it's just that we it's like a kind of a confidence thing. So in this case, because 0.5 would mean that is because we only, so you are onto something. We only had 2 classes, but what does that mean, right? So when you have 2 classes, it means that in order for one class to be the most, they have to at least be 0.5, right? If one class is less than 0.5, that means the other class is more than 0.5 in a Bernoulli trial, or when you only have 2 classes, right? So if it's less than 0.5, that automatically means that the other class was more probable. Does that make sense? Just because in this case there were only 2 classes. I think that I see why that might have been confusing on the slides. We do want to go with the most probable one. So if you, for example, in this one, it was like 0.29. If you imagine that if the class of probability of having the disease was 0.29, that means the probability of not having it was like 0.703, something like that. So that not having the disease was actually more probable. So we are still sticking to our philosophy of choosing the most probable class. It's just the case that when there's 2 classes, that threshold becomes 0.5. But yeah, good question. Is there any more questions, or is that it? Are we good? it wouldn't become 0.5, would it? What do you mean? Do you want to come onto the stage and talk, or probability of C1 given X and probability of C2 doesn't necessarily add to 1. No, but the question itself asked to classify it, meaning the only classification we're looking at is this patient going to be classified into having the disease or not having the disease, meaning there was only 2 classes. So the probability of each class would add to 1 because either they have the disease or they don't have the disease. There's nothing else. There's no conditional probability involved in that part. Yeah, there's no, yeah. They don't sum to 1. No, they will all, like the sum of the classes will always sum to 1. So I assume what you're asking is, if we have, there could be 3 classes, like, I don't know, like, what is, I don't know, this one is very binary. Either they have the disease or not have the disease. But say instead you were, classifying them into different diseases, like, I don't know, what diseases could we have? Like, I don't know, asthma, diabetes, and like high blood pressure, right? You could have 3 diseases, and then if you're classifying them into each one, then you'd pick the one with the highest probability. But even in that one, there would be a threshold, and they would add up to 1 because there is not a class, as in everyone has to fall in a class. You get me? You can't not fall into one of the classes. You have to fall into at least one of the classes, or exactly one of the classes. Does that make sense? So it always adds to 1, which is why when there's 2 classes, the threshold is 0.5. When there's 3 classes, the threshold would be 0.3 recurring, because, if any of them are greater than 0.3 recurring in that case, then it would be the most probable one. I'm pretty sure. Yeah. Actually, no. Don't, if it's for 3, that doesn't hold. Yeah, because you could have another one that's like 0.6. Yeah. Basically, I think it's just 0.5. Threshold is always 0.5, because if any class is greater than 0.5, that means that no matter what the other classes are, it's going to be the highest one. So yeah, it's always just the highest one. Yeah, simple approach. Yeah, I think I'm deeping it too much. Just think of it as the highest class. Any more questions? The advantages of naive Bayes. That's here. So it's just essentially like the common sense ones. It's just simple and easy. It's what I mentioned at the start. Because of the naive assumption, it works well with large data sets, performs well on categorical and continuous features, fast training and prediction. Limitations of naive Bayes include the naive assumption of feature independence, which is rarely true in practice, as we saw with this fever example. It may perform poorly with highly correlated features, because highly correlated features means highly dependent features on each other, essentially. And it's sensitive to imbalanced data sets. Here are some applications of naive Bayes as well. It's commonly used in text classification, document categorization, a medical diagnosis, which is what we just used it for now, and recommendation systems. And we don't need to go into depth on these, but there are some types of naive Bayes, which is just Gaussian naive Bayes, multinomial naive Bayes, and Bernoulli naive Bayes. So right now would be an example of we did Bernoulli naive Bayes, since the features, we only had 2 features, right? Either cough or fever. Oh, We also had, I guess, neither would be an option, so it wouldn't be Bernoulli, because I guess a person can neither have a cough nor a fever. But yeah, advantages of yeah. So I hope that answers your question. I don't think we need to look at generative and discriminative classifiers in this topic, since that I don't think that's related to naive Bayes, but I can look into it if you want. No? Which is this? This is generative. This is a generative classifier. As you can see, generative classifiers focus on joint probabilities, whereas discriminative classifiers look more at like conditional probabilities. Generative means. Yeah. So exactly, generative means it creates a label, and discriminative means it splits up the data set. I think so. That's like a broad kind of analogy of it. I don't exactly know about generative and discriminative. It was one of the things that I was pretty. It seemed pretty vague. Um, but yeah, it's not to do with naive Bayes. It's not part of the topic. So if we're gonna discuss generative and discriminative classifiers, I will stop the recording here. But yeah, thanks guys for joining. I'm just gonna stop the recording.